Alright, so in this video what we're going to do is we're going to explore how we can carry out stoichiometric calculations for gases as opposed to solids and liquids. Now if you think back to when we first introduced stoichiometry, I had created this little flowchart here where basically what we said was that we can convert moles of a compound to molecules of a compound. And the conversion factor that we would use for that was Avogadro's number. And then I also said that we can convert from moles of a compound to the mass of a compound. And our conversion factor there was going to be the molar mass of that compound. Now, this is really helpful when we're talking about liquids and solids because we can put a liquid or a solid on a balance and accurately measure its mass. This is not quite as easy when we're talking about gases. With gases, it's much easier for us to measure things like volume and temperature and pressure. Okay, but mass, not so much. So, is there a way for us to do stoichiometry with gases that doesn't involve mass but uses these parameters that we do know how to measure or calculate? And the answer is yes. Typically, we can go from the volume of a gas, so the volume of the compound, to the number of moles of the compound using the gas law. Okay, so PV equals nRT. So the key variables here being the volume and the number of moles. So you can imagine being given a problem where instead of being told the amount of a reactant in grams, you're given the volume of a reactant in, say, liters or milliliters. And then instead of predicting the mass of a product, you would predict the volume of a product produced. All right, so consider the problem that I just wrote down here, where we're being asked how many liters of water vapor can be produced by the reaction of 1.5 liters of O2 and 2 liters of H2. So the reaction that we're looking at is one that we've seen in the past, where we take hydrogen gas and oxygen gas and produce water vapor. Now, in the past, if we were doing a stoichiometry problem, we would look for the mass of H2 that we started with and the mass of O2 that we started with. We'd do a limiting reagent problem and then figure out how much water is going to be produced, typically in grams. But these are all gases. Okay, so in a problem like this, we would be given extra information, like we would be told that it's at a pressure of 1.10 atmospheres and a temperature of, say, 120 degrees Celsius. Okay, now, just like we've had to do in the past, we still need to do a calculation to figure out the proper number of moles of each reactant that's going to react. So we're going to have a 2 in front of the water and a 2 in front of the H2. All right, so here's how things are going to differ from what we're used to. Okay, we're going to first figure out how much product can be produced from the amounts of hydrogen and the amounts of oxygen that we're given. Okay, so we're going to go from the volume of O2 instead of the mass of O2, we start with the volume of O2, and we're going to convert that to moles of O2. Okay, with our conversion factor being the ideal gas law, PV equals nRT. Then we can go from moles of O2 to moles of H2O. And then for moles of H2O, we can go to the volume of H2O. Okay, and then we're going to do the same thing for hydrogen. And what we're going to do is figure out which one of these is going to produce the least amount of product. In other words, figure out which one of these is the limiting reagent. So, starting off with 1.5 liters of O2. We know that we are at 120 degrees Celsius. That's our temperature. Okay, we have a volume, which is up there. We have a pressure, which is 1.10 atmospheres. Okay, and what we want to figure out is the number of moles. So PV equals nRT. N equals PV over RT. Of course, we have to remember that our units have to be the correct units for our gas constant. So instead of having degrees Celsius, we have to convert to Kelvin. Okay, and that works out to be 393 Kelvin. So now we just plug these values in. So we get 1.10, and that's, nope, not liters, that's ATMs, times the volume, which was 1.5 liters, divided by the gas constant, which is 0.0821 liter atmospheres per mole Kelvin, times the temperature, which is 393 Kelvin. All right, and when I plug all this into my calculator, I wind up with 0.0511 moles of the O2. Next, I'm going to do the exact same thing for the hydrogen, except with hydrogen, we're starting off with 2.00 liters. That's our volume. Okay, we're still going to be using the same temperature, so the 393 Kelvin stays. Same thing for pressure. You can't have two different substances at different pressures in the same container. They can have different partial pressures, but the overall pressure that we're experiencing is going to be universal to all of them. So again, we plug these into our calculation. So our pressure is 1.10. Volume is 2.00. Our gas constant, 0.0821. And then our temperature is 393 Kelvin. Okay, and we figure that means we are adding 0.0915 moles of H2. Okay, now that's just the beginning here, because now we need to do the rest of the stoichiometry problem, which involves us predicting how much H2O can be produced from this. Okay, so if I have 0.0511 moles of oxygen, if I look at my balanced equation, I find that I can produce 2 moles of water for every 1 mole of O2. All right, and we can see here that this will work out to be 0.102 moles of H2O. Okay, and then we can do the same type of calculation for hydrogen. Okay, except we know that we can make 2 moles of H2O for every 2 moles of H2. Okay, which tells us that we can make 0.0915 moles of water with the H2 that we have. Okay, which means this must be our limiting reagent, the H2. Okay, so then, once we figured out that number of moles of water, we plug this into our gas equation. Again, PV equals nRT. This time we're going to solve for volume. So V equals nRT over P. Okay, we plug in the number of moles. Okay, we plug in the value for our gas constant. Plug in our temperature. And then our pressure. And then we feed this all into a calculator. And I wind up with the volume equaling 2.68 liters. Okay, and that's of water vapor that can be produced. Okay, so that's how we can kind of combine our knowledge of gas laws with stoichiometry to do these types of calculations.